So, special relativity, Lorentz transformation. Instead of the Galilean transformation, x prime equals x minus vt, it's simply x prime equals gamma x minus vt, where gamma equals 1 over the square root of 1 minus v squared over c squared. Remember that we have this term beta v over c, which is a unitless velocity quantity, but anyway, v, it just tells you how fast something is moving relative to the speed of light. Right? C is the speed of light. And gamma is the Lorentz factor, gamma, which changes things. But in addition, what comes out of this, and this is what's a surprise, particularly a surprise, is that time is no longer absolute. And that's the part of relativity that is kind of unexpected or bizarre or whatever you want to call it. Time is not absolute. And so instead of having t prime equal t in the Galilean transformation, we've now got, if we change frames of reference, time changes. And so therefore the movies like Interstellar, where they show time travel, are correct, is that you can actually travel forward through time at a different rate than other people can travel forward through time. You still can't travel back in time, but you can travel forward in time. Anyway, so it's t minus v over c squared x. And so this all leads to these basic ideas in special relativity of length contraction and time dilation. Length contraction and time dilation. Remember what those are. That length contraction says that there's a proper length, and the proper length is the length of an object when you are stationary relative to that object. But if you move relative to that object is going to appear shorter. Or if that object moves relative to you, just relativity, then it's going to not appear shorter, it is shorter. It would be measured as being shorter. It's not an appearance, it is actually shorter in your moving frame of reference. Same idea behind time dilation, right? It's not just an appearance, it's an actuality. You can age at different rates by traveling at high speeds relative to somebody. That's the idea about going forward in time relative to someone else. Time dilation says that there's a proper time between two events, and the proper time is measured by a clock which is present at both events, and anybody who moves relative to that frame of reference that has the clock present at both events measures a different time, which is shorter. Shorter? I think so. Yeah, that's right, shorter, because moving clocks run slow. That's the idea behind moving clocks run slow. So you should understand those. I didn't write down anything for those, but those you should understand and be able to apply. You will probably be asked to do that for a basic length contraction time dilation problem on proper time versus another time, and proper length versus another length on the senior exam. And then there's also addition of velocities, right? Where before we had the addition of velocity was, which I've crossed out at the bottom here, no longer holds. It's now different. It's a little bit more complicated. But basically, bottom line is that at low speeds, it still looks like a Galilean transformation. Velocities add, but at high speeds, they don't anymore. Doesn't matter if it's light or something else. At high speeds, they don't add like a Galilean transformation. And if you're approaching the speed of light, then they don't add at all. And that just comes from the equations for addition of velocities. So you can go ahead and review examples of those basic examples of length contraction, time dilation, and addition of velocities, and you will need to for the homework probably. So that's basically the kinematics, and then we move on to the dynamics of special relativity, right? And that's where we have momentum. It's still special relativity. Whoops, hold on. Energy and momentum in special relativity, where it turns out that that these things are very mass, energy, and momentum actually are very closely connected, right? This concept that E equals mc squared is actually gives us what's that actually is the rest energy. So you got to be careful about that. E0 equals mc squared is the rest energy, but in general, E squared equals p squared c squared plus m squared c to the fourth. And so if it's not moving, right? P is equal to 0, and so E equals mc squared. So E squared equals m squared c to the fourth, or E equals mc squared. That's with the rest energy when it's not moving. And this tells us that mass has an equivalence, that there is no difference between mass and energy. Mass is energy, energy is mass. It also tells us a number of other relationships, but this also okay, sorry, let me, I just wrote down some stuff, and so I'll start that sentence again. We already said the top part that I wrote down here, rest energy is mc squared. That means if something's, that's just telling us that this equation, if something isn't moving, then it still has a certain amount of energy due to the fact that it has mass. Mass is a form of energy. But this equation also tells us, and this comes up for photons, when we start to talk about the concept of a photon, for example, is that there's such a thing as a massless particle. If m equals 0, then you find that E equals pc from this relationship that Einstein gave us, right? So this is a much more important relationship than E equals mc squared. And what that tells us, interestingly, we didn't really do much with it, but is that a massless particle still has momentum, right? Momentum isn't a quality of having mass. It's a quality of having energy. So we used this only a little bit. We didn't go into a lot of depth, but in particular, right, it's what predicts the fact that we can get nuclear energy if we split a particle. That some of that, if we split an atom, so if we split a nucleus, some of the mass of the nucleus can turn into energy, and that's where nuclear energy comes from. Sometimes the process is backwards. If you take two nuclei and you attach them together, which is very difficult to do, that's called fusion, that the mass of the result is less than the mass that you started with, and that's because some of the mass turned into energy. That's the sort of important takeaway, one of the important takeaways, other than the theoretical interest in this concept on this page. So that pretty much covers it for relativity. There's other things in relativity that for different classes I've spent different amounts of time on that aren't the most important things in the world to remember. Things like the invariant quantities and space-time diagrams and stuff like that. Good stuff to be aware of, but certainly not going to be tested on. And the concept of light-like, space-like, and time-like, etc. Okay. Then we moved on in this class, and this is a good time to move on. Well, we talked about waves. I sort of put waves into Physics 116, but we really talk about waves in this class. Talk about waves and sound because quantum mechanics is dependent on waves. So we actually take this information that's on this page here and we start to talk about the properties of massless particles, which also can be treated like waves, and we connect that to the basics of waves and sound. So let's move on to the introduction to quantum mechanics.